Good afternoon, everyone. My name is Jean-Michel Tin, and I serve as a cybersecurity coordinator for the Center of Transportation, Cybersecurity and Resiliency, better known as TraCR. For those who have joined us today for the first time, TraCR is a U.S. Department of Transportation funded National University Transportation Center, led by Clemson University in collaboration with 9 other universities across the nation. The director of the center is Dr. Chowdhury. So now it is my pleasure to leave the floor to Dr. Chowdhury to begin today's session.
Thank you, John. It's my pleasure to welcome James Lambert. I have known him for a long time. When I was a student at UVA, he was doing postdoc, so he helped me a lot on my dissertation. So I owe a great deal to him. Dr. Lambert was awarded the 2025 10th annual Aspen Institute Italia Award. In 2024, the Distinguished Educator Award from the Society of Risk Analysis, and in 2023, the Best Paper Award of the 30th International Conference on Systems Engineering. He's a general co-chair of the 11th IEEE International Conference on Control, Decision, and Information Technologies. He was the chair of 8th Engineering Systems Symposium, which held in Charlottesville, chair of the 5th World Congress on Risk, president of the SRA between 2015 and 2016, the chair of SRA annual meeting, which was attended by over 800 participants, held in Washington, D.C. He is a fellow of AAAS, fellow of IEEE, fellow of ASE, fellow of SRA, and board certified by the American Academy of Water Resource Engineers. And he's a licensed professional engineer. He is a editor-in-chief of the Springer Journal, Environmental Systems and Decisions, and area editor of the Wiley Journal on Risk Analysis, and associate editor of the IEEE Open Journal of Systems Engineering. He received his PhD and MS from the University of Virginia and BSc from Princeton University. It's my pleasure to welcome Jim to the talk. So Jim, we are eagerly waiting to hear from you.
Oh, thank you everyone for joining. Thank you for inviting me, Dr. Chowdhury, and I look forward to continued partnership of our institutions and research centers. And you have asked me in this talk to focus on my activities in cybersecurity, systems engineering, and I'll do that. The trajectory of this talk is I'm going to tell you some of the theory and methods we do in our group here at the University of Virginia, and then I assure you by about middle of the talk, I'll begin talking about our cybersecurity center called NSF Chest Center. You see the name of it on this slide. And the where we are in 2025, it's worth recalling 100 years ago, there were some philosophers who began to cut up the newspapers. That was the text that they had. There were no computers, of course. They cut them up and then they rearranged the letters and decided that that was the forecast of what could happen in a future day, week, month, or year, or decade. And we are, with all the latest LLMs and the rest around us in engineering, it's important to recall that philosophical movement découpé and know that it is really what this talk ought to be about. I wish I could tell you more about it. I'm thinking about it every day and have some other projects on the side. I look forward to meeting you all about what we're doing with the machine learning and AI. But less on that now. And in this current talk, I want to remind, even though I'm headed toward a cybersecurity talk, that we have moved a lot of earth and resources and materials. And this is both our, it's all of our past and present and future is understanding as transportation engineers and other variety of systems engineers. What's the meaning of it all is the weight of history. As well, I like to think of systems engineering as a discipline where we are working on unprecedented challenges, that we are not building, replicating projects from history, but we have unprecedented requirements, unprecedented technologies, unprecedented opportunities and challenges. And this is roughly, Jean-Michel, you could help me. Those who know where they're going from the start will never go far. And this was maybe among the first modern systems engineers, Napoleon thinking of grand challenges and all those jargon that's up in the upper right. I was studied mechanical engineering as an undergrad, and I met this individual around 1986. He presented the master plan of the US Navy to develop antimatter propulsion, and it needed mining or searching for antimatter over decades and maybe hundreds of years. And this was my introduction to systems engineering. Before this, I'd been studying heat transfer and material properties and solid mechanics, fluid mechanics, and the rest. So I like to think of Robert Forward as I'm giving this talk today. And then my department chair passed away suddenly in the fall, and Dr. Chowdhury knew him well, as maybe some of you, Bill Shearer, and he had a big influence on all I'm about to say as well. We miss him at UVA, and we're mourning him, but thinking about with gratitude of the base that he made in our Department of Systems Engineering. And in a recent, about 6 months ago, relevant to what I'm going to show you in this talk, I was part of a group of NATO scientists. We met in Bulgaria, interested in how would a society in Central Europe and elsewhere come back from adverse conditions with its digital economy and digital systems. So this was, I was in charge of the working group that asked how new capabilities of AI would enable these Ukraine and others to come back. And the theme of that entire workshop was the resilience. And here was a sample of my working group. We're working on book chapters even this month and last month. So I'm letting you know what I'm doing moment to moment is working on resilience through digital technologies. These are more of those collaborators in my working group. And it's the best education is to be, have some international partners, international engagement. We learn best about Virginia and South Carolina, the region, and the United States when we get thousands of miles away. So let me tell you what's closest to my philosophy, theory, and methods is I've already told you some of what systems engineering, and the other is in the title of my talk, ambiguity. But first, I am interested to know a system not only for its inputs and outputs, its functions and missions, but for the order and orders of its components. And its components, those are sometimes the projects on the horizon, the new investments. Some it's the policies. We order, schedule the implementation of new policies. And some we are maintaining and inspecting and tracking current assets of our system and putting those in order of urgent needs for maintenance and the rest. And of course, the people are in some order, as well our partners in the enterprise, they're in some systemic order. So this, I'm telling you, a theme of my work to be on a fast track is to recognize any system for its component orders and to understand how those orders evolve from Monday to Tuesday to next week, month, and year, and the rest. And here's a slide I used at a recent meeting about which technologies renewable and others were going to be implemented in what schedule. As well, I'm as much as I'm interested in systems as a concept of unprecedentedness and the orders of those systems, I'm interested in what lies between and among sets of requirements. So, for example, I have a set of mechanical requirements from solid mechanics, and I have a set of thermal requirements. I have a set of energy requirements. I'm very much interested in the between of those sets of requirements. And in addressing what's between, I encountered this theory of interduality. It's Professor Hames that Dr. Chowdhury knew well. He had a flavor of this called phantom system models. And then Dr. Chen had a use for this theory. And I'm hoping to do more of that, understanding what lies between. And this is another way to say it is between the real and the imaginary, but I'm being more finding that more confining. I would like all of you, every one of you, to investigate the mathematical theory of this. It's an example of that is this summary paper from around 2013 describing what's the interduality or interdual, defining this crevice between system understandings. And then here are the examples of that in my experience with the Society for Risk Analysis is that on one hand, and now I encourage you to flip. You might believe what I'm telling you is real, and what I've labeled as imaginary is the real. So the column headings here are some way interchangeable, but I like to reflect on. Let's take the last row of this table and the theory of expected utilities, von Neumann and Morgenstern, is that a value in the von Neumann-Morgenstern, it's equivalent to a degree of uncertainty. So that's exchange hypothesis. And then the next to last row, that severity in risk analysis equates or is equivalent, exchangeable with system order. The next row above, I say any expert is valued or understood by the scenario or scenarios that they bring. So in a way, I'm taking a human being and understanding or mirroring that expert, that human expert, by their scenarios. I like as well the row above, the equivalence or the communication between environment and health. Above that is what I alluded to a slide or two ago, is that a requirement is only there to be traded for another requirement. So we'll trade speed for weight, or we'll trade energy for the information content, and that's a activity of systems engineering. As well, the row above that is anytime there's an event space in risk analysis, that's the basis of probability. I'm thinking who wins and who loses. So populations, subpopulations, the most exposed individuals, those are exchangeable or in a mirror relationship with the event spaces. And this is the most beautiful one, because some of you come from the study of multiple criteria, is I challenge anyone to have more than one aim or goal or ideal in mind at once. So to have multiple criteria, there has to be time, and a millisecond has to evolve to the next millisecond. That's the only way to have multiple criteria. So the exchangeability or the peculiar relationship of time and multi-criteria optimization. The one above that is very familiar to us in as duality in optimization, the exchangeability of constraints for goals. That is, an objective becomes a constraint and vice versa. And the top one, I'll say more about that later. Here's another picture of the same slide. The point of it being what lies between the real and the imaginary, or what lies between those columns on the previous slide. That's an interest that's very practical, and you might see some of that coming in the talk. Back to Earth is, with my students, I've been very interested in how to govern dozens and hundreds or even thousands of risk analyses. That constitutes a risk safety or cybersecurity program. We need to understand, are the meteorites a threat, the solar storms, or is it agricultural disease, cyber attack? What risks are addressed by this program? What are the resources and what are the outcomes that we monitor in order to grow the program, sustain it into the future? So that's some of my work here on Earth. This is a direction of work I'm about to show you. Is all these interpretations of risk analysis and resilience. They've been from the nuclear field, probability and severity. My first mentors, they taught me of risk management. What are the limitations or constraints on future options? When all the engineers work met schools and banks and hospitals, then the ISO said, well, this will work across domains beyond engineering. So it's the effect of uncertainty on objectives and the spread or the volatility of hitting a mark. That's the ISO interpretation. And then all I'm going to show you here on is I'm asking, how do hypotheses from the title of this talk and scenarios, how do they influence evolving priorities? So that's what's coming up, the volatility, the change of order, of system order. And being in a arts-oriented institution, we're very open to sources of threat and disruption, stressors from cyber, which is one of the, I'm going to tell you more coming up, but also from human behaviors, password habits, and so on, with changes from the environment. And Department of Defense, Homeland Security, and others are, of course, very concerned with obsolescence and how do we manage the diminution of one technology and its replacement by a future technology, and changes of regulation, rules, and rules of business processes and other. So all these are hybrid threats and hybrid stressors of large-scale systems. This is a processor of hypotheses. I'm interested in what are the hypotheses that matter. So and those that matter, they disrupt system order. I have some example coming up. The influence of hypotheses to system order, that's how I understand complex systems. And of course, Amazon has winked off in China. So that makes this even more of a touching chart, what I'm about to show you. But it's a ordering of tens, hundreds, and thousands of Amazon entities that were constituting Amazon in China. And this is the way to reach the boardroom. You say, I'm a systems engineer. I know a bit of decision and uncertainty analysis, all the rest, and that checks some boxes. But the best you can tell any member of a board or a CEO is how their partners are going to be different in a week and in 10 weeks and all into the future. How their products are going to be in a different order of urgency or schedule off into the future. How their partners, how their services, how their sources of revenue, all those are orders that are volatile into the future. And it's no different in the interest of the TraCR Center is for cybersecurity, knowing the system orders and how they might evolve. That's the point of this slide 24. And here's a sample of my work on order in a supply chain. These are all on the left, the vertical axis. These are all nodes of a supply chain subject to cyber and other threats. And the hypotheses drive the order. The order of these entities, their criticality is represented by the dark icon. So you see a couple of them at the top were tied for first place, and then the others are stacked through 20. These are all warehouses, communications, transportation, hubs, nodes, segments of rail, and all the rest. And the disruption of system order means they go toward the red, and when they go down in order. And then other hypotheses, they promote them in order in the blue. So this is the basis for what I told you, I promised you earlier. It's a basis for negotiation, is understanding that the schedule or the urgency or the priority under one hypothesis is some way different than under the hypothesis of another individual. And maybe it's the light that's between the interdual that's going to be what matters. But this is the mountaintop of the talk, honestly, is the decrease of system order represented by the red, and the increase in system order of the elements of this complex system represented in the blue. When we add it all up, aggregate, and one of the metrics useful to this is called Kendall's tau statistic. I can compare any order to the baseline. In this system analysis that we did, the pandemic was most disruptive overall to system order relative to a baseline order. You see cyber threats are the hypothesis of increasing cyber attacks. It was over to the right. Now, if we change conditions and change the system, the focus, then these results would move around. But this was a sample of what we're after, is what are the hypotheses that most and least matter to system order? We're still on the mountaintop of this talk. What are the hypotheses that influence system order? And what are those that are less of an influence to the system orders? All right, I've set the stage with philosophy, theory, and methods. Let me tell you some about this NSF Chess Center, as Professor Chowdhury has encouraged me. We are the largest industry, university, cooperative research center of the National Science Foundation at this time. There's 6 universities that are part of this. UVA, I'm the site director at UVA, but also Northeastern University, University of Connecticut, University of Texas at Dallas, University of California, Davis, and the University of Cincinnati. These are the 6 institutions that make up our center, and we're roughly interested for Internet of Things, digital security, hardware security, and trust. Let me tell you more about this center. So we have about 24 industry members that pay annual fee, the largest being the Air Force research laboratory, but there are all these others in the orbit and dues paying. They share in the intellectual property developed at the 6 universities and fund a tranche of projects every year. We're in about our 6th year, and the newest members are Amazon Supply Chain, Honeywell, and some others. So this is all the aim of the NSF is to involve universities and industry, and some of these UVA brought to the advisory industry board, and some of the other universities brought. And these are well, it's interesting to me because I'm on here, but maybe less to you all. These are the site directors of the NSF chest. Most of them are electrical engineers, and University of Virginia is bringing the systems viewpoint. And this is my book with some collaborators. What you all know in TraCR well is systems engineering, systems optimization, and the rest. In the NSF chest, we are, UVA is showing here as legacy systems. Do you see, I'm almost a footnote, the UVA Center, but integrated systems, legacy systems. And then our partners in this, they're working on topics such as if there's a board and someone's able to monitor its use of energy, use of its heat that it throws off, is it going to reveal anything about the operations of some large-scale system? Or if this board chip is lost, can it be reverse engineered by an adversary? Or same if the board or chip of adversary falls into the hands of the NSF chest investigators, can they reverse what were its functions and the rest? And anti-tampering comes to the front of this. How do we know that a particular board, chip, or piece came from a particular factory? What's the ways of authentication? And what are the intersections of all of the above with physical security? So you get here a sample of what we meet twice a year in the NSF chest, and these are the gravity of the projects done by the universities. Here's another picture of that. Our latest projects at UVA have been interested in counterfeiting anywhere in the supply chain. What does it mean to have a partially working piece, a counterfeit, that has some functions but others questionable? That's and how do we trust the entire supply chain with knowledge that there may be counterfeits? So this is another picture of the same overview of chest topics. Now, what does it mean? It's very stymieing. This is just 1 year of projects. What does it mean to have the largest chest center? In 1 year, we fund 20-some projects across the 6 universities. And this is an example of one of the calendar year tranches of projects. So you see some of the terms that I showed you at a high level. You see trust occurring in here. And these are all proposed by the industry members and by the Air Force and industry, government, and military. But then the university PIs, they volunteer to do the project. And these projects are anywhere from 50K to 150K, 200K. So these are the smaller projects, but they add up to those themes that I showed you. And I'll pause here just for a second to say we're doing the work, but we're publishing it all. So I'll send these slides to Ronnie, but these are with my collaborators at UVA Publishing. Now, it's good to have the overview, but let me show you what our latest active project. It's a 2-year project related to the Port of Virginia. We are asking, what are all the IoT devices inside the fence of the port, and what do chest technologies bring to the evaluation and countermeasures for security threats and vulnerabilities. So I'll tell you some about a single project. It is, in order to get this larger project, it built on 4 projects that we did from year 1, year 2, year 3, and year 4. So I'm going to tell you about this year 6 project, but give credit to these. These are all other UVA projects. You can see what it took to get to the big one. The Port of Virginia, it has a lot of electrification and motors, and that's the concern for the NSF chest and this project is the controllers of those motors. Do they give off any information that's should be private, personal, confidential, that should not be outside the fences of the port? And not alone, the port that we deal with, and most of the major ports of the United States send their manufacturing to China or bring it back from China with the motors installed. So this is the question: could the controllers be tampered with in some unforeseen way? And then how to know that what goes is sent to be installed overseas comes back intact and the same as when it left the United States. So this, and it's also interesting for the Coast Guard and others that do navigation near to the port. And all of this is colliding with the need for renewable technologies. Technology is moving at a rapid pace. I'll tell you some about that coming up. Here's a overview of the port and the containers and the movement of containers by automation. Lots of electric motors in moving vehicles, cranes, and the rest. I'll tell you more of that coming up. Here's another piece of the Port of Virginia. And those blue cranes are the ones that are a principal interest. They're manufactured overseas in Central Europe and Asia, and with the IoT parts on them. Here's more of the same, the large, the complex system. Here they are moving on a ship from to and fro from Asia and Central Europe. And this I've already told you about how to take stock of all the inventory of IoT devices, not only the motor controllers, all else with boards and chips, and nowhere chest has anything to say that can help out the port. So these are the steps of our holistic process, is using some risk analysis, resilience models and methods from the 1950s forward, but updating it with the interduality that I've described to you. This is just some of the urgency of it, of the same news media that you all are aware in transportation. Lots is happening with renewable electric and IoT devices. So this is vehicles that roll around with some of this automation, controls, how many computing bits and pieces are on a single truck. And not only the vehicles, but the charging systems that are vulnerability, the transforming of power from storage to running the motors and the controllers. And the charging can occur wireless, and it can occur as the vehicle is moving. So this is a exciting place to be, is understanding where freight is, and that's, I'm sure it's an interest for the TraCR Center. So here's a summary of all the locations of those devices in the port and for its partners. And here's a characteristic quad chart that every one of those projects that I showed you overviewing the chess center has such a project and schedule. You can see that it's underway through May 2026, that we're roughly getting started in January 2025 on this project. And Dr. Collier at Radford University, he's a fellow and co-founder of the CHEST from his UVA days. He's very much part of this project. So that's an overview. I hope we'll have some publications in the next months. As I'm bringing this talk to a conclusion, I want to remind you that with the TraCR Center, we're part of IEEE, Society of Civil Engineering, the Society for Risk Analysis, the MCDM Society that we owe a lot to INCOSI and its systems engineering body of knowledge. These are our all the principles of cybersecurity for transportation and other infrastructure. It derives from good ground in systems engineering. I hope you all will join me. I'm a general co-chair of this meeting upcoming in Croatia this summer in July. We're going to bring some of these work on NSF CHEST and other work with my other sponsors, research sponsors, to the CODIT meeting. It's my third meeting with this group, and it's owing to IEEE and its 700,000 members, the success of this meeting on control and decision technologies. As well, I may see you at George Mason University hosting the CSUN Symposium in June of 2025. We hosted this meeting at UVA in 2021 in the fall, coming out of the pandemic, and had the speakers on the right. And George Mason is doing a terrific lift in 2025 to have the latest version of the CSUN, and maybe Clemson, Texas, and the other members of TraCR are interested for the CSUN itself. So let me remind you, I'm trying to think philosophically with you about systems engineering, the imaginary, the real, and what lies between in the negotiation of requirements and trading of requirements in systems engineering. And the I'm doing not only this cybersecurity, but I'm working on Olympics, and grid blackout was a big topic, radiological emergency. I've worked with runway safety for the FAA, and then also with 5G technologies. All of this with the same themes of system order and disruption of that order by hypotheses, with the ambiguity of requirements, ambiguity of missions and purpose, and the risk programs. So thanks to Zach particularly for introducing UVA to NSF CHEST, and I hope you'll visit us in Charlottesville anytime. I'm grateful for being invited to the TraCR today, and look forward to any discussion. Thank you very much.
Dr. Lambert,
Yes, I can hear you.
thank you very much for your presentation. Now we can proceed to the question answer session. If anyone has a question, you can send it to the chat box and I can relay it to Dr. Lambert.
Dr. Lambert, I have a question. So on you showed NSF CHEST research topics, for example, side channel analysis, and then detecting adversarial circuit in any device. So every project you showed there, we are involved in some fashion. Our TraCR is doing projects on those topics. So
Yes.
is there a way we can collaborate? Because exactly the same projects you showed, we have something going on in each of the topics.
Absolutely, Ronnie. I'm so interested for that, and the challenge I have, and maybe TraCR has a similar, is that the experts at the level of the chips, we need to introduce them to the owners of these complex systems at the Air Force, where they might have an entire base, and the Port of Virginia, or auto manufacturing facility, or a chemical manufacturing facility, because they don't naturally speak the same jargon and terms. So that's maybe how our systems and risk communities are adding value, is to be the helpful intermediary to work from the at all these scales, from the micro, nano to the level of a military base.
Okay.
Thank you for the question. It's very great one.
Thank you.
We have one question. So, okay. So this question is asking, who is the lead from UT Dallas for your IUCRC?
Oh, very good. Yeah, so that's Professor Yorgos Makros, and he's Professor Makris helped us. He hosted the one of the NSF chest sites, and they're adjacent to, some of you know better than I do, they're adjacent to Hewlett Packard, who donated much of their campus, and their engineering dean hosted us there, and she's alum of UVA Systems Engineering. So it was a great day. We are all friends, including with Clemson. So thank you for the question.
Yeah, it was Dr. Turasingham who asked that question.
Yeah, so
Can I say something? Yes, he's yeah, I know him very well, and he's very good. And also, it's the Texas Instruments that that really
Thank
supports
you.
the engineering school. Yeah.
Thank you very much. Yes, I misspoke
Thanks.
entirely. It's Texas Instruments. That was my first calculator. I should not have forgotten it. It was 1978.
Thank you.
I had that.
By the way, I said excellent talk. I really enjoyed it.
Thank you so much for
Very good,
joining.
yeah.
Thank you very much.
you can either write your question in the chat box,
Yeah.
or you can ask
Directly as well.
in real
yeah.
time directly.
There's another question,
Oh,
Jean-Michel.
thank you. It was
Dr.
Dean. I think your dean is Stephanie Adams. So she's
Stephanie Adams. Yes.
she's
Wonderful
alum
lady,
of
yeah.
UVA. I don't know if you knew from our system.
Yes,
program.
she was at Texas A&M for the PhD, and she was at UVA, I think, for the master's.
Masters. Yeah, what a wonderful
Yes.
scientist and engineer. Thank
Yeah. There was another question, Jean-Michel, from Hadi Amini. I think he had his hand up.
Okay.
Yeah, thank you, Dr. Lambert. Very impressive talk. So I have a question about the notion of interduality. So is there a connection between this notion and what we have in optimization theory when we try to develop a dual problem and then solve it, especially in linear programming? So how do you see the connection between this notion of interduality and duality in the classic sense that we have in optimization?
Yeah, so it's so good because same as you, I met this interduality, but I didn't know I was meeting it when we were taught about the dual problem in linear programming. So there's and then the objective becomes the constraint, and it reaches to the same result. But I think what to understand about interduality, and that's that mathematical theory that I showed here, is that it's really neither the objective nor the constraint, but it's the space between them that is an appropriate focus. And that's maybe what the systems thinking is ultimately about, is the ambiguity of being neither the objective, neither the constraint, but the manipulating the space between them. So that's where is the dream of these scientists who came up with the interduality, is the focus is on the inter rather than what you and I met as duality. So I hope that's some way helpful, and that you'll look with me at this paper. It's more like a 10-page exposition of what I just described.
Very interesting. Thank you. I'm going to read that paper actually.
Thank you. And it's a free one. I don't think it's behind any paywall, so it's good access to it. Thank you for the question.
If Dr. Lambert, if we are cybersecurity is all about real-time systems and have some countermeasures implemented right away, so I see that risk analysis has a value because you can identify potential attack surfaces, a probability of that being attacked, that surface. But where else you see that because systems is a lot of analysis, a lot of stochastic systems, because we want some quick solution. But how do you see the role of very comprehensive analysis? Like
Very good. I think
yeah.
this, it's such a good question.
Practicality, yeah.
Yeah, practically, this is where I believe is where we begin. At least when I work with the chest scientists, I say, okay, we need some inventory of all the IoT devices inside your fence, inside the responsibility of the port. And then what's the baseline understanding, as if you're the EPA or other and you have an endangered species list, or the FBI and you have the most wanted list, or the another EPA is to have the list of the top toxic materials. So that's the beginning, the baseline. And you, as you said, it can be done very quickly. Give me the list. That's your baseline. And then we have a place to begin adding hypotheses, disruptive hypotheses. And the list is then movable, changeable, negotiable. And that's the point of this slide that I showed. So I would say the first thing to do is replace what's on the left here with these nodes of the supply chain, replace that with the IoT devices and classes of IoT devices, and see what's the disruption from the variety of hypotheses. And I think those hypotheses, of course, they include trends in technology, but also human and operator behaviors, also the markets and supply, also the regulations that are on the horizon, and the tariffs is another one. How are tariffs going to affect the urgency, criticality of these devices within the footprint of a port or other facility? So I hope this is and why this is fast. Imagine you had to derive the importance of these devices from some massive input-output model that had the goals of the port and the goals of GDP and the other goals of society. You'd never arrive. But we can always start with the list, characterize the system by its baseline order, and and that order being subject to disruption. So thank you. You got right to the heart of the efficiency and the fast track of this approach. Very good.
And I'm assuming that the system that we are investigating for cyber threats, so they already may have a diagram, the architecture. So in addition to what resources they have, assets they have, so they will have how the system is working now in terms of the port. So that will also be an input, the system architecture.
Yes, no different than when I created this chart with the Chinese, is that we rarely develop a system from nowhere. It's more, we arrive to one that's already in place. And so, so all this that I described, the baseline, it's already on the shelf, and it's needing, you make the request, what are the orders that characterize this system? People, places, entities, assets, projects, policies, locations, all that.
That makes sense. Thank you. Thank you.
Thank you.
Let's see if we have another question. I don't think we have any more questions.
So we are close to the end time and we don't have any more question. Audience members, any question or? So doesn't seem to be any more question. Thank you, Dr. Lambert. It was wonderful. I learned a lot, so I'm sure audience members learned a lot. Thank you.
Thank you for inviting me. I'll see you all very soon.
Thank you.
Thank you, everyone.
Bye.
Thank you. Bye.
Bye.
Thank
I
you.
will share the video probably by the beginning of next week. I will upload it on our YouTube channel.
Thank you.
Thank you.
Thank you.